Hi everybody and welcome to another video in the deep learning audio application from design to deployment. In this video, we're gonna build our simple speech recognition system, and for doing that, we're gonna use TensorFlow and Keras. Specifically, what we're gonna do is basically building the design, the architecture of a convolutional neural network. Then we're gonna compile it, then we're gonna train it, test it, and save it so that we can reuse it during inference. Good. One note that I want to stress here is that I'm not going to go too much into the details of what a CNN or convolutional neural network is, how it works, and a bunch of different things like regularization or dropout layers, this kind of things. And that's because I have a whole video series there that's called Deep Learning for Audio with Python. So if you're interested into getting a very good detailed teaching about that, so you should go check that out. It should be over here, so you can click that. Cool. Okay, so let's get started. So the first thing that I want to do is just provide the high level entry point to to the process that we will be covering here. So I'm gonna build a function that's called main, and here we're gonna do a bunch of different things. So the first one is gonna be basically load the train, validation, and test data splits. Then as a next step, we are gonna build the CNN model. So here we're going to build the neural network. Then we are going to train the model, and we are going to evaluate the model using the test sets. And finally, we're going to save the model. Good. Okay, so let's get started from the first step here. So here what I want to obtain is the inputs and the outputs, or the target labels for a training. And specifically, we're going to have this for three different data splits. So one is for training, one for validation, and one for test. So here we're going to have X train, X validation, X test, and then we are going to have Y train, Y validation, and Y test. And this is equal to a function that we still haven't implemented, but I'm going to put it here as a placeholder. So, and we can call it get data splits. And this function takes an argument that's a data path. Good. So this data path over here is a constant that we should write here. And it's basically the path to this data.json file that we've extracted in the previous video. And it's basically the file where we have all the labels and the MFCCs and the mappings. Okay, and so this is equal to data.json. Good. Okay, so once we've loaded these the train, validation, and test data splits, then we need to build the CNN model. Okay, so if we're doing that, we are gonna create another function, and again, I'm gonna just use this function here as a placeholder, and then we're gonna implement both this and get data splits. So here we are gonna have this model that's equal to a function that we'll call build CNN, for example, or yeah, let's call it build model to be consistent. And here we're going to pass in a couple of arguments. So one is the input shape, And the other one is the learning rate. And we're going to use a constant here, and I'm going to define the learning rate, which is the basically a parameter that we used in the optimization algorithm, and we're going to use Adam as our optimizer. And I'm going to set this equal to 0.0001, which is a quite customary value to have as a learning rate. Good. So what about the input shape? Well, the input shape is the shape of the input data that we are feeding into our CNN. So, and in order to get that, we need to extract that value over here. And we are gonna extract it from X train. So this X train is going to be an ND array. So we can take the shape of this NumPy array and then pass in the X train shape at index 1 for the first dimension of our input shape, and then we can just take this and put it equal to 2, and then here equal to 3. Now, let's understand what we are doing here. So we need a 3-dimensional array, and the reason why is because we'll be dealing with a convolutional neural net that takes a 3-dimensional input. So the first dimension that we have is given by the number of segments. So if you guys remember, in the last video, we extracted MFCCs at equally spaced segments, and the length of a segment was given by the sample rate, or the total amount of samples that we had in our audio files divided by the hop length. And so this will give us the number of segments that we have. Then the second dimension is given by the number of coefficients that we extract, and in our case this was equal to 13. So we extracted 13 MFCCs. And finally we have the third dimension, which is set to 1. So this third dimension, as I was mentioning, is fundamental for a CNN, and that's because it's the dimension that carries information about the depth or the so-called channel of an image. And in case, for example, of a grayscale image, the depth this dimension is equal to 1. If we had a RGB image, this channel would be equal to 3. But given we are dealing with audio data and MFCCs in particular, so it's as if we were dealing with with some data, just like a grayscale image. So just depth equal to 1, so 1 channel. Good. So this is the input shape, and so here we build a model passing in the input shape and the learning rate. Great. So as I said, we don't have build model, we don't have get data splits. We're going to implement this in a while, but before I want to go through all the code here at higher level. So now that we've built the model, we need to train our speech recognition system. And in order to do that, we can use a method that comes directly from the Keras API, and it's called fit. So we do a model dot fit, and here we need to pass in a bunch of different arguments. So first of all, obviously we'll need to pass the training data. So X train and Y train, so both the inputs and the outputs. Then we need to specify the number of epochs that we want our network to train for, and we'll set this equal to a constant called capital epochs, and we'll set this equal to 40. So now what's an epoch? Well, an epoch basically let's say the number of epochs tells us how many times the network is gonna see the whole data set for training purposes. So in this case, we set this epoch to 40, which basically means that we're going to pass the dataset for training purposes 40 times through like the network. Good. And then we have another value here that another argument, which we'll call, well, that's called batch size, and we'll set this equal to batch size, yet another constant that we'll set here equal to 32. So the batch size specifies the number of samples that the network will see before an update and running like the backpropagation algorithm. So basically running like a learning step. Good. Okay, so we have this, and then the last thing that we want to pass in is the validation data. So this is validation validation data, and this is obviously equal to X validation and Y validation. Now, yeah, this is getting too far. Good. Okay, so with this basically running model.fit, we're gonna train our speech recognition system. So now that we've trained the system, we should evaluate its performance on the test set. And so we're going to get back from this evaluation process a test error, that's also called loss. And we are also going to get back a test accuracy. And so this is equal to model.evaluate, where evaluate is another method coming from the Keras API. And here we should pass X test and Y test. Good. So this way we can evaluate the model. But now if we want to see the results of this evaluation process, so we can print the test error and the test accuracy. And so I'll do a test error, test error that's basically equal to, and I'll pass in test error, and then I'll do a test accuracy over here, and I'll pass in the test accuracy. Good. And finally, we want to save this model. And so for saving this, we'll use yet another method from Keras that's called model dot, not surprisingly, save. And what we should pass here is the saved data, saved model path. Okay, so this is another constant that we can specify over here. So we'll set it equal to model.h5. So this is just the path to the model that we want to save. And so we'll save this in the current directory, and we'll save it in this format, which is h5, that's used by Keras. Good. Okay, so here we have the whole high-level process. So just to summarize what we've done, we are going to load the train validation test data splits as the first step. Then we're going to build the CNN model, which is our keyword spotting system. Then we'll train this model, evaluate the model, and finally we'll save it so that we can load it when we need to do inference or prediction. Good. Okay, so now we have a couple of major things we should do. So we should define this function, get data splits, and this function called build model. Okay, so let's start from get data splits. Okay, so we'll do it over here, and here we know that we have an argument that's data path so the path to the dataset. And here we should do a bunch of things. So first of all, we want to load the dataset. So we want to load both the input and the targets. Then we need to create the train, validation, and test splits. And as we'll see in a moment, this the train, validation, test splits, or I should say, the inputs of the train, validation, and test splits are going to be two-dimensional arrays because they come from the data.json file over here. It's basically these MFCCs here. And so we need to convert these two-dimensional arrays into three-dimensional arrays. And so we should say converts inputs from 2D to 3D arrays. And then we can return all the data splits. Good. Okay, so now that we have a plan, we should just implement the code that will enable us to enact it. Okay, so load dataset. So what we expect here is X, so all the inputs, and Y, all the labels or the output targets that we expect. And in order to do that, we'll call another function that we need to create that's called load dataset. And here we should pass this data path. Okay, so now let's implement this load dataset function first before moving on. Okay, so this is we define load dataset, and we know that it accepts this data path argument. And so here, what we should do is load the data.json file. And for doing that, we know that we need to import the JSON module. And so here we'll do a with open. So we open the data at the dataset. So we pass in the path to the data.json file. And we want to open this in a reading mode because we want to read from data.json. And we'll open this as FP. And then we'll do a data. It's equal to JSON.load, and then we'll pass in FP. So basically we are loading the data set and storing it in this data variable. Right. Okay, so now we need to extract inputs and targets, right? So the X and Y's. Okay, so X is going to be equal to data, the data dictionary, and then we are gonna take data in MFCCs. And this is because, if you guys remember from the previous video, I was storing these MFCCs here in a list called MFCCs. And so this way we can get our inputs. And for our outputs, we're going to do a data labels. And again, guys, if we go back here, at some point over here, yes, we are retrieving this labels key. That's a list in itself. Good. Okay. And now we can return X and Y. So my question is, are we done with loading the dataset? Well, not really. The reason is because we want for this inputs and labels over here to be NumPy arrays, whereas this things that we've extracted, so data, MFCCs and data labels are Python lists. So we need to convert these lists into arrays, NumPy arrays. So for doing that, first of all, we need to import a NumPy as NP. Now, if you guys don't have a NumPy installed, that's super quick to fix because you can open the terminal and do a pip install NumPy and you're all good to go. Great. Okay, so let's get back here. So how do we cast a Python list to arrays? Well, we do a np.array and then we just pass in the Python list, in this case the MFCCs, and we'll do the same thing over here, passing to numpy.array the labels or the targets. Great. So now X and Y are NumPy arrays, and so we can return them. And if we go back here to get dataset splits, now we see that load dataset should work fine. So now we have our X's and Y's. Oops, sorry. Okay, so I had an issue with my microphone here. Okay, so here we have our X's and Y's. So the next step is to create train, validation, and test splits. Right. So what we're doing here is basically dividing the data set into 3 splits. One is going to be used only for training, another one for validation, and the third one for test. So now we do this so that we can train the neural network like on some data, then validate that data on a different validation split. And we could use this validation split for doing optimization on hyperparameters and things like this. We are not going to do that, but I'm going to include this validation split here because it's the way things like should be done, it's like the best way of like doing things, really. And then we are going to keep like the test split as a completely separate split, and that is like the test split that you're going to use only like when you're done with all of your optimization and improvements on the validation and the train splits. Good. Okay, so let's get that. So we'll do so what we want to build here is a X train, then we want to get X test, and then Y train and Y test. So we basically want to split the original data set, so the X and Y, into X train, X test, Y train, Y test. So how do we do that? Well, we could basically build like this separator like from scratch, but there's a very handy function that comes from the scikit-learn library that does that for us basically for free. And so we want to import that. And so we'll do from scikit-learn model selection imports train test split. Now, if you're not familiar with scikit-learn, this is like this standard traditional machine learning library in Python. Again, if you don't have this installed, you can just open your terminal, do a pip install scikit-learn, and you should be good to go. Great. Okay, so now we have this train test split function over here, and that's what we want to use here. So we are going to pass in the inputs, the outputs, and then we should specify the test size. So what's the test size? Well, the test size tells us what's the proportion of the data set that's going to be allocated to the test set. Okay, so we'll put this, let's expose this value. So we'll just create this, use this variable here that we're going to input over here in the arguments of our getDataSplits function, and we'll default this to 0.1. So 10% of the dataset is going to be used for testing purposes, which basically means that the X train and Y train are going to be 90% of the dataset. Okay, but this isn't done yet because we want to still do another split. So we're going to reuse train test split for dividing the training set that now we have, that's basically 90% of the data set, into training and validation. So what we should do basically is just like the same thing here, but instead of doing X train X test, here we're going to do an X train X validation and Y train Y validation. So the train test split here we should pass in X train and Y train, and then the test size over here we are going to create a new variable that we'll call test validation. Now, yeah, let me just put this to a new line. Okay, so this test validation, that's going to tell us the proportion of the training set that's going to be used for validation purposes. And so I want to expose this one as well. So, and I'm going to put this to 10%. So in our case, this is going to be 10% of the 90%. So, which basically means that in the end, we're going to have the validation split is going to be equal to 9% of the overall data set. Good. Okay, so now we should have all of our splits, so the train, validation, and test splits. So the next thing that we want to do is to convert these inputs from 2D to 3D arrays. So first of all, I want to show you like what we have like currently. So currently, like the size or the shape of X train and X test and X validation is a two-dimensional array. So where we have a number of segments, that's the first dimension, and 13, which is the number of MFCCs that we've extracted, as the second dimension. So we want to add a third dimension and 1 as the third dimension. So how do we do that? Well, NumPy can help us doing that super easily, because we'll do a X train that's equal to X train, and then we're going to use this convention here. So we'll put this like 3 dots here, which basically means give me all the stuff, like all the dimensions like so far in the array, and then add like a new dimension using this instruction here. So np numpy.newAxis. Cool. So we are going to do the same thing for X validation here, and again, we'll do the same thing for X test. Great. Okay, so here we are basically done. So we need just to return these guys here. So we'll do a return. And so we are returning all the different data splits. And so if we go back to main, now we know like that we've just like completed this get data splits function, and so now we are at this level. So build the CNN model, and so we know that what's missing here is this build model function, and so we need to implement this. Good. Okay, so we'll define build model, and we know that build model accepts a couple of arguments. So one is the input shape, and the other one is the learning. That's mistyped. Learning rate over here. Good. Okay. So this is another like quite complex function to build, but let's start like from the highest level possible. So here we should do a couple of things. So one is just like build the network. So we need just like to craft it from scratch and put all the layers in. And the second thing that we should do here is to compile the model. And this is required by Keras. Okay, so here we're going to use like TensorFlow and Keras. And so like the first thing that we want to do here is to import TensorFlow.Keras, and we'll import this as Keras. Okay, so what's the difference between TensorFlow and Keras? Well, TensorFlow is the low-level deep learning library on top of which Keras is built and works. Well, it's not true that Keras is built on top of TensorFlow, because it works also like on other like lower level deep learning libraries like Theano, for example. But basically the idea is that the TensorFlow provides us the deep learning library, and it does like all the operations like on tensors and things like that. And Keras is an API. It's kind of like a wrapper on top of TensorFlow, and it's very like user friendly, and so you can build very complex stuff using like a very simple instructions. So that's why we are like using Keras. Now, if you don't have TensorFlow installed, once again, you can pip install TensorFlow like this, and then you can install it, right? But installing TensorFlow can be a little bit of a hassle depending on the flavor of TensorFlow that you are installing. So you can install TensorFlow both for CPU and GPU. When you install it for GPU, yeah, it's a little bit of a hassle. There are like a bunch of like different things that you should do. I'm not gonna cover them because they're also like very different depending on whether like you are on Windows, like Mac, or Linux, like I am. And by the way, I'm using TensorFlow CPU here, so you can easily use TensorFlow CPU here as well without like bothering about setting up TensorFlow for GPU, like for like these tutorials. Good. Okay, so let's build this network. So the first thing that we want to do is create a sequential model. So we'll do Keras.sequential. So a sequential model, not surprisingly, is a neural network that has a bunch of like sequential layers. So one leads into the other, and the new one leads into like a third one, and so on and so forth. Good. Okay, so now let's take a look at the type of neural network that we are going to build. So this is a convolutional neural network. Again, I'm not going to go into the details of what a convolutional network is, because like it's outside of scope of this a series, which is more interested into like the overall workflow from design to deployment, and mainly deployment, I would say. But if you're interested, I have like a video where I have the theory of a CNN, and then there's also another video that I have that gives you like an idea of how to implement a CNN and discusses like all of those things more in detail. Okay. So we said we are going to have like a CNN here for our speech recognition system. And so we are going to have 3 convolutional layers. So we're going to build conv layer 1, conv layer 2, conv layer 3. And then, we are basically flatten the output of the conv of these like convolutional layers and feed it into a dense layer. So we're going to have a dense layer after these 3 convolutional layers. And after that, the last thing that we're going to have is another dense layer with a soft max classifier. Good. So now we need to build all of these things. Okay, so let's start with the first convolutional layer. So we'll do a model.add, and the add method in Keras is the one that enables us like to add, not surprisingly, really like things to our layers, to our model. So the layer that we want to add here is the keras.layers.conv2d. So it's a convolutional layer. And so here we should pass in a bunch of different arguments. So the first one is the number of filters that we're going to have. And so here we're going to have 64 filters. Then we should specify the kernel size, which is basically the size of these filters. And this is going to be a 3x3 filter. Then we need to specify the activation function that we are going to be using. And we are going to use a rectified linear unit here. Then we want to specify, let me just go to, to a new line. We need to specify the input shape, and the input shape here is this input shape guy here, which is our argument from build model. Good, and we need to specify this because we are at the first layer, and so Keras needs to know the shape of our input here. Okay, and finally, I'm gonna add here a regularizer, specifically a L2 regularizer. Again, this is something that I'm not gonna explain, and it's kind of like quite complex, like mathematically, and I covered it like in another video where I was talking about how to improve like your models, and specifically like to tackle the issue of overfitting. And L2 regularization is one of those techniques that you can use to tackle that, and to like just like make training like more stable and improve your models. Okay, so that we can do in Keras very easily, because we can call Keras, then regularizers, and here L2, and here we this like L2 regularization accepts a parameter that we're gonna set equal to 0.001. Good. Okay, so this is the convolutional layer, like the first thing like itself. And then after this, we are gonna add another layer that does a batch normalization. So batch normalization is another technique that we use to speed up training and to get like better results. So for having a batch normalization layer, so we'll just do keras.layers.batch normalization, and we are done. And after this, we are gonna add another layer, and this time it's gonna be max pooling. So we'll do a max pool to the layer. And so here we need to pass in a bunch of variables, arguments in as well. So the pool size, which is going to be 2 by 2. So basically what max pooling does is it downsamples the output of the convolutional layer. And with the size of, so here we have like the pool size, which is like 2 by 2. And then we use strides, again, that's 2 by 2. And we are gonna add padding that's equal to same. Again, I'm not getting into the details here. So if you want to like learn more about all of these different types of like layers, regularization techniques, just go back to my deep learning for radio with Python series. There I just like go very much in details into like all of these things. But all you need to know like really here is that this max pooling layer is basically like downsampling by a factor of 2 the output from the convolutional layer. Great. Okay, so this is all we need for the conv layer 1. Okay, so conv layer 2 is quite similar to conv layer 1. The only difference is that I'm going to have 32 filters over here, and I don't need this input shape anymore because that's only needed for the initial layer. And so I can just like get all of this, copy and paste it for conv layer 3. This time we are gonna change a couple of things. So we are gonna change the kernel over here, and we're gonna set it to 2. It's a 2 by 2 kernel. Now I've just realized that like in this architecture, like for the first 2 convolutional layers, I want a pool size that's 3 by 3, not 2 by 2, and then I'm gonna have a pool size of 2 by 2 only like here, like in the third convolutional layer. So yeah, I've just fixed that. Good. Okay, so here we are at the end of the third convolutional layer. So the next step that we want to do is take this output, which is a 3-dimensional output, and flatten it to a 1-dimensional array. Why should we do that? Well, because dense layers need a 1D array as input. So in order to do that, we are gonna add another layer that's called flatten. It's as simple as that. So with this, we are flattening our output. And then here we can pass in another layer that's a dense layer this time. So it's a fully connected layer, and so it's called keras.layers.dense, and here we should pass a bunch of arguments. So the first one is the number of units or neurons, and we'll set this to 64, and then we should specify the activation function that we want, and here we'll use again ReLU or rectified linear units. Now, for the first time, you're going to see another type of layer that's called dropout. And this is yet another technique to tackle overfitting. And so so the dropout layer takes a parameter, that's the dropout rate, and we'll set this to 0.3. So basically what dropout does is it shuts down in this case, 30% of the neurons in the dense layer during like training, and this is done like stochastically. So now you may be asking, say, why do we do that? Well, it turns out that if you do this thing, what happens is that the network doesn't necessarily rely on one or a few neurons for doing classification, but rather the network should adapt, and all the different neurons should take equal responsibility for the classification itself, which is a good thing. Good. Okay, so now we had this dense layer, and now we are finally at the output layer, which is a softmax layer, which, by the way, is another way of saying that we want another dense layer, but with an activation function that this time around is going to be a softmax function. So we'll do this, and then here we should specify the number of units that we want, and this is going to be equal to number of keywords. Right, so what's this number of keywords? So we'll set this as a constant over here, and we'll set this equal to 10. So these are like all the different keywords that we have in our dataset. So it's equivalent like to down, off, on, no. It's this 10 keywords. And so basically we have this 10 different neurons in the output layer. And then we'll use as an activation function, we'll use soft max. Okay, so what the softmax layer is going to output is an array. And here in the array, we're going to have like as many values and scores for the different number of keywords that we have. Okay, so we know that we have like 10 different keywords, but for sake of simplicity, let's assume we only have 3 keywords. Okay, say yes, no, off. So an output could be something like this: 0.1, 0.7, and 0.2. So these basically are the scores for the predictions. And so like we for like choosing like which prediction, which keyword we like the input like audio file is actually going to be, we're going to get like the index that has the highest score. And you can think of like these scores as probabilities, because if you add them up, if you add all of them up, you are going to have a result of 1. Good. So this is like what softmax does. And it's the way we're going to decide how to pick like the different predictions. Good. So now we are done building like this quite, relatively complex like CNN. Good. Okay, so the next step is to compile the model. So for compiling the model, the first thing that we want to do is choose an optimizer. And the optimizer comes again from Keras. So as you can see, basically Keras is taking care of all the difficult stuff that go under the hood in deep learning. So we're going to have Keras optimizers, and we're going to use Adam, which is a quite efficient optimizer. And we are going to pass in our learning rate, which is this variable that comes from, this argument here, and that's accepted by the build model function. Okay, so we have the optimizer here, and then to compile the model, what we're going to do is quite simple. It's a model.compile. This is yet again another a method that comes like natively with Keras. And so here we should specify a bunch of things. Obviously, the first thing is the optimizer with a Z, and we'll assign our optimizer with an S to it. Then the second thing that we should specify here is the loss or the error function that we are going to use. And now I want to expose this, and I'm going to call it error. And I want to expose this so that the whole thing becomes like more modular. And error here, we're going to default this to sparse categorical cross entropy, which is like the loss function or error function that we're going to use here. And finally, here in this compile method, where we are going to also specify the metrics that we want to track, and we are going to track accuracy during training. Good. Okay, so now we've compiled the model. So the last thing that, I'd say like it could be nice to have like an overview of the model. So let's say we want print model overview. And so for doing that, we'll do a model.summary. And obviously we need to return the model here. Good. Okay. So it seems we are done. So let's revise like this main function and how like the whole workflow works. And so first thing that we do is we load the data set, and then we split it into train, validation, test, and data splits. Then we build the CNN model. Then we train the model. Then over here, we evaluate the model on the test split. And finally, we save the model. So if I haven't made any mistakes, which is probably I've made a few, the code like should work. So now I'm just gonna run this and see what happens. But for running this, we should do what the good kids, Python kids do, which is if name is equal to main, then we are gonna run main over here. Cool. Okay, so let's run this and see what happens. Okay, so over here it's taking a little bit of time because obviously it's loading a lot of data. So we should wait a few seconds here. And yeah. Nope. We have an issue over here. We have an issue with, oh yes, nice one. So I'm wondering if you guys have found this like error, like while I was like typing this in, but it's not MFFCs, but it's MFCCs, which stands for mel frequency substrate coefficients. Good. Okay, so let's rerun this and see what happens. Okay, again, yeah, we should wait a little bit. So, yes, it's working. And it started like the training process, and over here you can see the model.summary function in in function. And so here we have like the whole summary like of our model over here, and here like you'll see like our model training. So here we have like the different epochs, and now we know that already after the first epoch, we have validation, an accuracy on the validation set that's equal almost to 60%. So this is like quite good. So now I'm gonna post this video because it's gonna take some time to train the whole model through like 40 epochs, and then I'm gonna just get back once everything is done. And here we are back with our result for the training process. And as you can see here, we reached a quite good accuracy overall. And on the test set, we have 95% accuracy, which is remarkably good for such a simple network that we've built like very, very quickly. And so the other thing that I want to show to you is the model itself that's been saved over here in the current folder we are working. And it's over here as model.h5. So the next thing that we are going to do, and this is going to happen in the next video, so we are going to use this model.h5, we are going to load it and make prediction with it. So the focus of next video is going to be on inference and basically building the whole keyword spotting service. Good. Okay, so that's it for today. I hope you've enjoyed this video. I know it's quite long, but I feel like you might have learned quite a lot today. So if you've liked the video, please remember to leave a like. And if you want to have more videos like this, remember to subscribe and hit the notification bell. So it's everything for today. I guess I'll see you next time. Cheers.